Extreme Physics.
Let's talk about resistivity. Here I have a spool of copper wire, right? You got a big old spool of copper wire, and it's made out of copper. That's why it's called copper wire. And resistivity is a material property. It describes how easily charge can move through, like copper. You know, if I understood the resistivity of copper, and then I took a hunk of this copper and cut it off, if I understood the material property, the resistivity of this individual hunk of copper has a resistance. I could calculate the resistance of this hunk of copper by knowing that it's made out of copper and by understanding its dimensions. It has a length and a cross-sectional area, and by knowing that it's copper and its dimensions, I can figure out what would the resistance to the flow of charge be of this hunk of wire. So let's say I had a hunk of wire like this, and we're going to be calculating the resistances of cylinders, right? Because wires, basically, it's a cylinder. And it turns out that if I had a hunk of wire like this, the resistance to the flow of charge is going to be the resistivity. Rho is the resistivity. That thing looks kind of like a P. It's not a P. It's a Greek symbol, rho, times the length, right? The longer the length, the higher the resistance, divided by the cross-sectional area, right? The wider this is, the easier it is to put charge through. It's just like a hose or a straw or something like that. A straw, a really long straw, is going to have a high resistance to the flow of air through it, and a skinny straw will also have a high resistance to the flow. If it's a fatter straw, it's going to have less resistance. So there you go. So resistance of a hunk of material, of conductor, is going to be the resistivity, which is the material property, times the length divided by the cross-sectional area. All right. Resistivity is the difficulty. It's a material property, and it's the difficulty in which charges move in a material. It's strictly a material property. It's different than resistance. Resistance actually describes a device. Those little resistors I showed you in the I don't know if you saw that. I had that tuner opened up and there were a bunch of resistors. Those were resistors, and they have a resistance to the flow. This is resistivity. This describes the material that you might build a resistor out of. Like copper has a resistivity. Gold has a resistivity. Silver does. And it describes how good a conductor are those things. So resistivity is the difficulty in which charges move in a material. Electrons do not move easily in materials with high resistivity. And as temperature goes up, conductors have increased resistivity. Usually the temperature really has to go up significantly before it changes significantly. And most resistors don't significantly change their resistance with temperature under normal operating conditions. So here we have a hunk of wire or something, some sort of conductor, and we can see we have an electron bouncing through. Now, we often draw the charges going through like that, nice straight line. Well, they don't do that. They're bouncing all over the place. They're bouncing from molecule to molecule, and they tend to go in a certain direction, and that's called the drift velocity, but it's certainly not a straight line. They're bouncing around all over the place. All right, so if it's going this way, that means there must have been an electric field in the opposite direction. This is an electron. And the electric field is defined as a direction a positive charge would experience a force. So if the electron's experiencing a force to the right, the electric field must be to the left. And of course, this is also the direction of the current, to the left, even though the electrons are moving to the right, because current is defined as a direction positive charges move. All right, so if we have a hunk of material we know what it's made out of and we know its geometry, we can calculate its resistivity, its resistance, pretty easily. And the resistance, like of this cylinder, this it looks like a hunk of wire, is rho. That's the resistivity. This is the material property. This describes what kind of material it is. L is the length, and A is a cross-sectional area. And this equation kind of makes sense that the longer something is, the higher the resistance. If you've ever tried to blow through a garden hose or something like that, it's really long and it's really hard to blow through, to move air through it. A straw is much easier because it's shorter, even though the cross-sectional area of a straw is significantly less than a hose, but its length is much less, so its resistance to the flow of air is less. And inversely proportional to the cross-sectional area. So the larger the cross-sectional area, the wider this is, right? The bigger the cross-sectional area, the easier it is to move stuff through. And that's true of straws too, right? If you got a big normal straw, and you breathe through it, you can actually move air through it pretty easily. But if you got one of those little Capri Sun straws, those real dinky ones, they have a very small cross-sectional area, and it's hard to move a lot of stuff through that quickly because there's a lot of resistance to flow. So this is in your reference table, and let's use this. It's kind of straightforward. Rho is the resistivity of the material. That's not P. That is a Greek symbol. It's rho. All right. So determine the resistance of a piece of copper wire that is 4 meters long and has a cross-sectional diameter of 2 millimeters. Assume a temperature of 20 degrees C. And if we look at our Regents reference table, we'll see the table says, it doesn't just say resistivity, it says resistivities at 20 degrees C. Okay, the fact that it says that implies that if you change the temperature, the resistivity will change. And indeed, that's the case. Resistivity will increase as temperature goes up. Usually you have to change the temperature significantly before you see a significant change in the resistivity. And certain materials really do change their temperature a lot, like nichrome. Nichrome's the little wires you see in your toaster, the ones that glow really orange because they get so hot they give off light. Those are nichrome wires. It stands for nickel chromium. And those actually, their resistivity will significantly change in use because the temperature changes so dramatically in use. Like this. All right. So the resistance equals rho L over A. All right. I hate these pens. It makes me look like I'm writing with my left hand while being smacked upside the head with a baseball bat. But anyway, so rho for copper, if we take a look at that, that is 1.72 times 10 to the minus 8th ohm meters. All right, so there we go. And the length is 4 meters, so we're going to multiply that by 4 meters. And the cross-sectional area is, they gave us a diameter. All right, well, I know the cross-sectional area. The area of something is pi r squared. So pi, if 2 millimeters is the diameter, then the radius must be 1 millimeter. 1 millimeters squared. All right. Punch that into the old calculator. 0.0219 ohms. All right, that's a low resistance, and I would expect a low resistance for copper. Copper is a good conductor. It's most wires are made out of copper, and 4 meters isn't very long, so I would expect a low resistance. So that seems like a reasonable value. Let's see what happens if we take a conductor and really raise its temperature up high. So I have a simulation here, and here you can see I have some charges, and have a battery, and they're just bouncing around because that's what they do. They're bouncing around. Everything's always moving. All subatomic particles are always bouncing around in random directions, and they're bouncing around. But you can see that it's really not flowing in any particular direction because there's no potential difference across the wire. I'm going to need to close the switch with the battery in there to get a potential difference. And if I close it, okay, so we could see that they continued to bounce around, but they tended to drift along one direction because of the battery. And those are supposed to be electrons, and I actually have them going backwards. But don't worry about that. Electrons should have gone this way. But anyways, so they did that. Now watch what happens if I do something similar, where I got my charges bouncing around, my subatomic particles bouncing around, and I close the switch, but now I'm going to get the conductor really hot. And let's see what happens. Okay, we can see that the current still flowed, but it's flowed at a lower rate. It was bouncing around more because of the excitement due to the higher thermal energy. Thermal energy is actually things just bouncing around more. So they're bouncing around. It made it harder to move the charges through the conductor, but they still did. If you take a look again, they are drifting this way, but just at a slower rate than they were when it was cool. You can see that those are moving much faster. So as the temperature goes up on a conductor, the resistivity also increases because it gets more difficult to move the charges through the conductor. Usually the temperature has to really increase significantly before we see this effect, but things like light bulbs, incandescent light bulbs, they really do get that hot. In fact, they get so hot they start giving off light. And their resistivity does increase with temperature. And if we take a look on our reference table, we see that we have a list of resistivities. And note it says at 20 degrees C. Okay, so that must be a clue that this changes at different temperatures, and indeed it does. And here are the resistivities of aluminum, copper, gold, nichrome, silver, and tungsten at 20 degrees C. But as the temperature goes up, the resistivity will also go up. And something like nichrome will really go up. Nichrome is actually those little wires you see in your toaster, the glow orange. That is stands for nickel chromium. That's nichrome wire. And that's designed to get really hot, and that will actually change significantly when you're toasting. You're making your little avocado toast in the morning. That will increase. Ohm's law. All right. Well, we have that relationship R equals V over I. Well, resistance usually remains constant for any device. The only time it really changes is if the temperature changes dramatically. But at constant temperature, the current through a conductor is directly proportional to the potential difference across its ends. So if I increase the voltage, the current increases. But the resistance remains constant. And in this case, we got potential difference versus current. And it goes through the origin. So this is a direct proportion. So the slope is V over I, which is resistance. So the slope is resistance, right? And that will remain constant as long as the temperature doesn't change significantly. And most conductors, they don't. Now, one exception to that is nichrome. If you take a look on your reference table, you got nichrome. That stands for nickel chromium. And that is the little orange wires in your toaster, where they glow orange anyways. They're not normally orange. They're more like a gray. And then you see them glow orange. They get so hot I mean, they get really hot that they actually give off light. That's pretty hot. Tungsten also is a little filaments in those incandescent light bulbs. They glow bright because they just get so hot they start giving off light. So with a light bulb, you would, if you slowly increase the voltage across a filament and light bulb, it's going to be linear for a while until it starts getting hot and starts glowing, and then the resistivity of the material is going to go up, so therefore the resistance of the light bulb is going to go up. So with a light bulb, it does become nonlinear because it gets so incredibly hot that as it goes up, as you increase the potential difference, the current doesn't go up as much because the resistance goes up. But most normal materials, under normal operating conditions, the voltage versus current graph will be linear and the resistance will remain constant.
History. Fans out.